Last time, obviously, we did a number of examples involving ice tables and how to solve ice tables. And again, a reminder, there's a few different ways that we saw. You could obviously use the quadratic. You could have a kind of perfect square situation. Or again, you could kind of assume x is equal to 0 and make an assumption. Remember that if you do make the assumption, you do need to check it. And we are rolling with the 5% rule here. And again, to check your assumption, you do take the x value that you get and you basically divide it by whatever you're going to kind of subtract it from or add it to. And you times it by 100%. And again, if it's sort of less than 5%, you're good to go with that assumption. If it is greater than 5%, then you do need to go back and sort of solve it another way. And for us, that probably would be the quadratic is where you probably need to go and sort of solve for that. Remember, the assumption doesn't work in all cases, and you really should only use the assumption when you have a small value of k. So again, you should not use the assumption on a large value of k because with the large value of k, you have mainly products, which means the change part is going to be relatively large. So you shouldn't do the assumption or anything like that. So any questions on any of that there? All right, so to finish up this chapter, the last thing we're going to talk about is Le Chatelier's principle. And Le Chatelier's principle is the idea where we have a system at equilibrium. And when we have a system at equilibrium, what's going to happen in this case is we will actually mess up the equilibrium here. And we will do something to that equilibrium that is going to essentially mess up the rate of the forward reaction equaling the rate of the reverse reaction. And that is when we add some type of stress to the system. So when we add some type of stress, it's going to really mess up that equilibrium. And because these reactions are pretty interesting, they will themselves want to return to that equilibrium state. And to do that when we kind of mess them up is they really kind of three options. Either they will kind of shift to the right, and when they shift to the right, that really means we're kind of making more products to get back to equilibrium. They may shift to the left, which means you need a little bit more reactants to get back to equilibrium. And there's also a few things that you could actually do that will, even though you kind of did something to it, it will cause really no change, no shift in the equilibrium sort of position. So what are sort of the stresses that we could do to a system at equilibrium? There are a few. There are things that involve concentration. We could do something that involves the pressure or the volume. We could do something that involves the temperature. And we could also add a catalyst. And these are sort of things that we can sort of apply to a system that's at equilibrium that may cause the system basically, again, to sort of shift one way or the other to try to get itself back to that equilibrium state. So we're going to talk about each of these and sort of the effect that it has on the equilibrium and what will happen in each of those cases. So let's start with concentration. And really, when we talk about concentration, there's kind of two things that you could really do. You could either add more, and when we add more sort of concentration, what typically happens is it will shift away from the side you added it to. So that means, if we add more reactants, it will go towards the products. If we add more products, it will go towards the reactants. So it always sort of goes away from whichever side you add it to. And when we're talking about sort of sides, we're obviously talking about the balanced equation. There's not really arrows and stuff in the beaker or anything like that. So when we think of the equation, that's when we're talking about kind of left-hand side or right-hand side. The other thing that you could do is actually remove, and you could remove some concentration, and that usually will shift towards the side you removed. Now, when we add more concentration, it's pretty simple. You just go grab a reagent off the shelf that has those ions in it, for example, and you just dump it in there. Or maybe you add some more gas or something to it, and you add something that's already in the equilibrium sort of reaction. Now, when we want to remove something, say we have ions floating around in a beaker and maybe we want to remove some ions, we obviously cannot just reach in with our hand and like pull out the ions because that's probably not recommended, right? So there are some ways that we can remove things from, say, an equilibrium. One way is, for example, we could add something to this that's not in the actual equilibrium we're looking at, but that will perhaps react with somebody that's floating around, and maybe it will make it into a solid at that point and form a precipitate. And as we know, solids are not included in the equilibrium, so that's essentially like reaching in there and pulling out that ion when you kind of precipitate it out as a solid. So that's one very common way that you could kind of remove something. Another very common way that you could remove something is, for example, if you had in here like hydroxide floating around, you could add like an acid. And if you add an acid has H plus and OH minus will make water. So that's another sort of way that you can sort of remove something from the equilibrium. As we also talked about, water is not part of the equilibrium. So if you have a solution that has either H plus floating around, you could add some base and that will make water and get rid of it. If you have something like hydroxide, like in this example, you could add something like an acid that will then make water and get rid of it as well. So if you have some type of equilibrium that has H plus or OH minus in it, you could actually form water by adding an acid or a base depending on the situation, and that will again effectively be removing those things. So when we add more, it does go away. So AA is a good way to remember that. And when you remove something, you could think of it like you made a hole on that side and you got to kind of fill it. So it'll come towards that hole and kind of fill it. So, for example, if we had, this is say the reactant, this is the product, and we had, a couple of classics stick figure guys. This is advanced stick figures. They have faces. Your basic stick figure here. So if we got these guys here and they're at equilibrium, for example, here, and let's just say somebody else hops on over here on the product side, that's going to cause this situation to occur, perhaps. And now that's not so good. To fix this problem, do we need more people on the left or more people on the right? Yeah, so we add it to the right, it's going to shift away, right? And we need to kind of put more people back over there on the right-hand side. Ran a little out of room there. We'll try to squeeze them in as best we can. We're just taking the picture from farther away, so they look smaller. There we go. And now it is back at equilibrium at this point. So again, it always kind of goes away from where we're adding. Same idea here. Again, if we had kind of the same situation to start with, reactants, products. This guy decides I'm going to hop off. I had enough of this ride. This is the situation that's going to happen now. In this case, we now need to put more people back to the right-hand side, right? The side where we removed it. And that's going to get us now back to equilibrium, right? And obviously the take-home message is probably don't be on this side of the thing here, right? Because that seems like the bad side. Any questions on that there? So add away and remove goes towards it. Like I said, sometimes it's good to think of if you remove something, big hole, got to go towards it to kind of fill the hole. And that's a good way to sort of remember it. Any questions on that there? So the next sort of thing that can affect sort of the equilibrium is pressure and volume. And they oftentimes are kind of tied together. And when we think about pressure and volume, perhaps we think about a classic gas law known as Boyle's law, right? And Boyle's law tells you that as the pressure goes up, what happens to the volume? Volume goes down, right? And vice versa, as the pressure goes down, volume goes up. So they are sort of tied together. As the pressure goes up, as a result of the volume going down, I personally like to think of these guys in terms of volume. And basically, if we have a small volume like this, and the pressure went up because of it, that's sort of the change that's occurring. The pressure started to increase. So we kind of want to bring the pressure back down. And in order to bring the pressure back down in a very small volume, would I need more or less gas molecules? I would need less gas molecules. Less gas molecules are going to cause less collisions. Less collisions is going to bring the pressure back down. So in this situation, it will shift to the side with the least number of gas molecules. And that does obviously depend on the reaction you're looking at as to if that's the left-hand side or the right-hand side. You basically go through the reaction and count up. Everybody's got a G next to it, count up their coefficients, and basically see which one has less gas molecules. Now, the opposite is sort of true here. If my pressure goes down, that means my volume goes up. So really the change that's happening in this situation is the pressure is starting to drop. So we kind of want to bring the pressure maybe back up. Here we now have a larger volume of area. That would require the opposite effect here. We would actually need more gas molecules in there to sort of bring the pressure back up. More gas molecules are going to cause more collisions. More collisions will kind of bring our pressure back up. So we'll go to more gas molecules. So this guy will shift to the side with the most gas molecules. So if you sort of think about it in relationship to volume, it's an easy thing to remember. If you have a small volume, small, less gas molecules. If you have a larger volume, more gas molecules. So that's a good way to sort of remember it as well. Any questions on that? What happens if I had, for example, equal gas molecules on each side? Would it shift anyway? It would not. That would be a situation where you could get a no change situation, as there is no side that's more or less. So even though you did something to it, it's not going to actually affect it. So there will be no change. So no change is a possible answer that you could have in a couple of situations, that being it. So if I had a reaction such as this, and I did the following things. What I want to know is, will it shift to the left, to the right, or will there be no change? If I do the following, let's say I add some D, I remove some A, I decrease the volume, thank you, increase the pressure, I add some B. So take a moment there for each of those. Which way? Bless you. All right, let's take a look. So we'll start the first one, which is we're going to add more D. So when we look at the reaction, D is over here on the product side. When we add, we shift away from it. So this should cause the equilibrium to shift to the left. The real reason why it's going to shift to the left is when we add more D, that is a product. That's going to cause the reverse reaction to occur because you now have more products than reactants. So that's going to really cause the reverse reaction here to occur. We're going to remove A. So A is a reactant. And when we remove A, and remove anything that goes towards the side we remove it from, which means this will also head to the left here. And the way you could think of it again is you kind of made a hole on that side, so you got to kind of fill the hole of where you removed it from. The real reason is obviously if we remove A, we once again now have more products than reactants, which means once again, that's going to kick off that reverse reaction occurring because again, you have actually more products than reactants, and that's why it's going to go towards the side you removed it from. If I decrease the volume, that means that my pressure is going to increase, right? Which these are actually the same in this case. That was a bad choice on my side. So when we do that, we want to look at the volume. And when we look at the volume, it's small volume, which means we actually need less gas molecules. And in this particular reaction, these are both gas molecules on the left-hand side. There's a 2 and a 3, which means you got 5 gas molecules over here. This is also a gas molecule. You got 4 gas molecules there. That would mean in this particular case, it would head towards the product side actually for both of those, since they're actually the same effect that occurred in that case. And again, in this reasoning here is obviously in a smaller volume, we now have a lot more of those reactants, going to have to kind of force it to go in the forward direction to get it to less gas molecules being present. Lastly, here we're going to add some B. B is a reactant. When we add it goes away, should shift to the right there. The reason, again, is in this case, when we add more B, which is a reactant, we now have more reactants than products, and that should kick off the forward direction in this reaction heading towards the products. Any questions on any of those there? All right, the next thing we're going to look at actually is temperature. And remember, temperature actually works the same as concentration. So it works really exactly like concentration, which means if we increase the temperature, it should shift away. And if we decrease the temperature, it should shift towards it. Do this, so arrows there. Now, how do we know really where temperature is? That has to do with what type of reaction you're dealing with. And that means that you are either dealing with a exothermic reaction, which means that heat and energy is released. And when we think about an exothermic reaction, because heat and energy is being released, we think of heat and energy as a product, like it's being given off. So in a exothermic type situation, we would consider basically the temperature, the heat or energy, or however you want to look at it, as being on the product side. So in an exothermic reaction, if we increase the temperature, it would shift to the left away from it. And if we threw everybody on some ice there, it would come towards it because that would be like removing heat and energy, and it would come towards the product side. Most of the time, I would say the way that, again, exothermic reactions and even endothermic reactions are related to you is you will be given the delta H value for it, which is the change in enthalpy. And a reminder that if you're dealing with an exothermic reaction, that number is going to be a negative number. So if you have a negative number for the delta H, it will tell you that basically you're dealing with an exothermic reaction. Endothermic, again, is sort of your other option there. And again, that is when heat and energy is absorbed. And in that case, we think of heat energy as more a reactant than a product. And once again, that means in an endothermic reaction, if you increase the temperature, put your test tubes in some hot water or something like that, we would expect it to shift to the right-hand side there towards the products. And if you put your like test tubes on ice and kind of cooled everything down, we would expect it to shift to the left in an endothermic. Also a reminder, delta H for an endothermic reaction is a positive number. So I would say probably 99 times out of 100, that's how they would sort of represent to you in a Le Chatelier's principle type of problem. If it's exothermic or endothermic, they'll just kind of give you the delta H value at the end of the reaction or equation, and it'll either be positive or negative, and that's how you could kind of make your determination. Any questions on that there? Now, the last thing that sort of can affect an equilibrium, not really, but is a catalyst. And as we talked about in the previous chapter, again, a catalyst is really, again, not a reactant. It is not a product. And it does not get used up in the reaction. It is there, as we talked about a lot of times, just to simply facilitate the reaction happening faster in most cases by finding that sort of more efficient way for that reaction to take place. In terms of Le Chatelier's principle, this is another way that you could kind of get a node change. You'll just get there quicker. It will not sort of cause it necessarily to shift one way or the other. So there's kind of like three ways that, like you could kind of get a node change. This is one way, as I mentioned a second ago, that if you have like equal numbers of gas molecules on each side, that's another way. And sometimes they like to throw in, like you throw in like a noble gas or something into the mix. And again, noble gases are chemically inert. They really don't react with other things. So that's also sometimes another way that you can kind of get a no change situation. Any questions on any of that there? So if we had, we'll do this. And we'll do like delta H is negative 125 kilojoules. All right, so for each of these, we want to know, obviously, will it shift to the left, will it shift to the right, or will there be no change if I decrease the pressure, I add A, I increase the temperature, I remove C, I add a catalyst, decrease the volume. I decrease the temperature here. And I add D. All right, give that a go, see what you come up with here. Okay, let's take a look. We'll start with the first one, which is we're going to decrease the pressure, which means really our volume is going to increase. So if you think about it in terms of volume, larger volume means more gas molecules. And in this case, I got like 4 gas molecules over here. And over here, I got 2 gas molecules, as that is a solid, right? So in this case, we are going to shift here to the left in this case, give us more gas molecules. We're going to add some A. A is a reactant, so by adding more A, what that's going to do basically is kick off the forward reaction. It goes away from the side we added. In this case, it should go to the right. If I decrease the temperature, in this case, this is my delta H value, which is a negative value. That means that this guy is exothermic, and that means we should think of heat and energy as a product. And in this case, if I lower the temperature, that'll be like removing products, which means then we have more reactants, and that's going to cause it to go fill that hole we just made over there and head in the forward direction, really towards where we removed it. Obviously here, opposite there, if we increase the temperature, it'd be like adding more products, and adding more products would cause the reverse reaction basically to occur, and it will go away from the side we added it to. Removing C, C is a product. You can think of it again as making a hole on that side. So we'll go towards it to fill the hole. Again, the real reason is as we remove the products, we now again have more reactants. That's going to cause the forward direction basically to occur in this case. We add some D, that's going to give us now more products, causing the reverse reaction, and it will shift away from where we added it to occur. We add a catalyst, not too much is going to happen here, so that's going to give us a no change. And lastly here, if we lower the volume, we would expect the pressure to increase in this case. And once again, with a smaller volume, we actually want less gas molecules to kind of bring the pressure back down. And in this case, that would be to the right. Yeah. Any questions on any of that there? Yeah. All right, let's take a look at just a few more here. Finished out here. Obviously, here we talked about it. Our concentration, again, shifts away from where you're at, goes towards it. K is really dependent on whether it is a exothermic or endothermic. And again, pressure and volume are really related to each other. And just thinking about the volume, small volume, less gas molecules, larger volume, more gas molecules is a good way to sort of remember that there. All right, so we got like a real one here. Let's just say the delta H for this reaction was, we'll go positive 325. Why not? That's clearly not it for sure. Let's see what happens here if we add NH3. We decrease the pressure. We increase the temperature. We remove H2. All right, let's give it a go. Okay, so let's take a look here. We're going to add more NH3. So that is a product. When we add, it goes away. So in this case, it should go to the left. Once again, we're adding more products, going to cause the reverse reaction basically to occur in this case as we have more products than reactants. We decrease the pressure. As we decrease the pressure, that means my volume is actually increasing. And in that case, we would need more gas molecules in this case to kind of bring the pressure back up. Left-hand side here, we got 4 gas molecules, and right-hand side, we have 2. Again, just counting the coefficients there. And that would mean we would need larger volume, more gas molecules should go to the left. Here we're going to increase the temperature. We look at our delta H. That is a positive one, which means it's an endothermic process. And that means that heat is considered a reactant in this case. So if we increase our reactant side, that means it should go away and should shift to the right, again, causing that forward reaction basically to occur. And lastly here, removing our H2, which is a reactant. Going to create a hole on the reactant side that we need to fill, so it's going to go towards where we removed it from. Again, the real reason is we now again have more products and reactants, going to cause that reverse reaction basically to occur. Any questions on any of those there? Yeah. All right, one last one here, perhaps. There we go. All right, so you don't have a coefficient, make sure you do there. We're going to do decrease pressure. We're going to decrease the temperature. We're going to add some N2 and remove some NO. And while we're at it, why don't we add another catalyst here just for fun? Okay, so lastly here, we're going to decrease the pressure. That means, again, my volume is going to increase. We then want to go to the side with more gas molecules. So here we got 2, and here we got 2. So that looks like a tie. So that's going to be a no change in this case, as again, there's no side with more gas molecules in this particular case. We're going to decrease the temperature. Endothermic means heat is a reactant. You can think of it that way. So we're going to remove this guy, which is like removing reactants, making a hole on the reactant side. Should shift to the left. Again, that's going to cause really the products to go in the reverse direction in this case. A catalyst, again, not going to cause a change either. as again, it'll just get you there quicker. Adding our N2 once again is going to increase our reactance, going to cause the forward reaction to occur and shift away from the side we added it from. And lastly here, removing our NO, going to cause a hole on this side that we need to fill, so it'll go towards it, but really you then have now more reactants than product, so it's going to head in the forward direction to fill that hole. Any questions on any of those? The Chatelier's principle? Yes. No. All right. That is it, huh? All right. So that is chapter 13, is it? Here, start with chapter 14. It is a long chapter. Eventually, we'll get through it. They throw everything into this chapter. So most books will split this chapter up into like two separate chapters. They put everything in one chapter in this book. So we're kind of going to do a part 1 and part 2 of chapter 14. And at some point, we'll just be begging to be done with chapter 14 after like 9 weeks and stuff. But I'm kidding. It's not really 9 weeks, but it feels like 9 weeks. All right. So acid and bases is what we're going to start talking about here in part 1 of this lecture. Um, and we're going to do everything from just basic acid and bases, pH. We'll talk about weak acids, weak bases. Then in the sort of second half of chapter 14, we'll get into everybody's favorite stuff, buffers, titrations, oh my, and we'll do all that good stuff. So let's talk about acids, like it's hiding behind the orange there, I think. So acids, they do have a sour taste. Try not to taste any acids in lab for sure. Vinegar owns its sort of taste to acetic acid. We have citric acid there in fruits. They react with certain metals, as you may be familiar with, in a single replacement reaction. So again, if you take something like magnesium and a little bit of hydrochloric acid, right? A little single replacement type of deal there. Going to kick out the hydrogen, make some magnesium chloride and a little hydrogen gas, which if you've done this, which I'm pretty sure you probably have at some point in your chemistry career, you probably saw some bubbles form along the way there. That's a really bad balancing job by myself there. That's why they invented erasers, I suppose. Put it in the wrong spot there. There you go. And again, it will kick out that hydrogen here and make some hydrogen gas. They also react with carbonates and bicarbonates to produce carbon dioxide. Again, if you took something like hydrochloric acid and reacted with some sodium carbonate, or sodium bicarbonate, we'll do a double displacement reaction, right? And you will make some H2CO3. And you'll also make a little sodium chloride in this case. And this will go through a decomposition reaction where we'll make water and some CO2 gas, basically, right? So plop, plop, fizz, fizz. It will kind of go away. Bases, on the other hand, they feel slippery. Many soaps are bases. A lot of drain cleaners are bases and stuff like that. Also a good idea, we'll just talk about really quickly here, just a reminder, when we talk about acids and naming acids, right? Um, it all involves whether or not there is oxygen, right? And when you go to name an acid, and if the answer is no, there is no oxygen in it, your acid should be something like hydro something ic acid, like HCl. That has no oxygen. That is hydrochloric acid. HBr, that is hydrobromic acid. By the way, acids typically have the aqueous symbol next to them to imply that they are in solution, which is essentially what makes something an acid, is that ability to kind of release that H plus in solution. If you do have oxygen, right, then you probably have everybody's second favorite thing, polyatomic ion present. And as you know, the polyatomic ions end in ate or ite usually. And if it is yes, and your polyatomic ion ends in ate, then it's something ic acid like HNO3. NO3 is NO3 minus, which is nitrate. This would be nitric acid. H2SO4. SO4 is sulfate. This would be sulfuric acid. And if your polyatomic ion ends in ite, your acid would be something OUS acid. And if you had something like HNO2, NO2 minus is nitrite. This would be nitrous acid. If you had H2SO3, SO3 is SO3 2 minus, which is sulfite. Be something like sulfurous acid. So hopefully you remember naming things like acids, and that way it's not like this thing, right? So you know what it is. Any questions on how to name acids? All right, so now that we refreshed our memory, hopefully, on how to go about naming acids, let's get into acids and bases here. So a early definition of an acid is the Arrhenius definition of an acid, and that is something that produces H plus or H3O plus in water. And that is really your definition of an acid is the ability to, in solution, which is why they're aqueous, have the ability to produce H plus that is freely floating around in that solution, not attached to anything else. And that's what makes something sort of an acid. When we talk about acid-base chemistry, pretty much H plus, which is the hydrogen ion, and H3O plus, which is the hydronium ion, is pretty much the same thing. You can use either one pretty much interchangeable, both in equations, both in formulas. I would say nowadays books tend to use H3O plus more than H plus, but I kind of use H plus a lot. So we'll use H plus. So pretty much anywhere I put H plus, you can basically exchange it for H3O plus. So why do we get like H plus or H3O plus? To be honest with you, we could just look at hydrochloric acid, for example, which is this first one here. And this is hydrochloric acid basically dissolving in water. And you absolutely could represent that equation like we see here and include water. And because we did include water in this case, because this is an acid, it's going to actually send a hydrogen ion over. And that is how we make H3O plus in this particular case. And that's how we get H3O plus. Now, because something like hydrochloric acid really is a strong acid, you could also represent this basically just hydrochloric acid in solution in water by just simply writing hydrochloric acid is going to break apart into H plus and Cl minus. And that's a perfectly fine representation of what is going on here. Here, I did not use water in my equation, which you don't really necessarily need to for acids. And I get H plus versus H3O plus, but it's basically the same thing. So it is really your preference. I'm okay with it, whichever way you want to do it. If you want to leave the water in there with the acids, you can. If you don't want to leave the water and just show it breaking apart into H plus, that's perfectly fine. Like I said, I probably will just do the H plus for a couple of reasons. And one of the reasons is later on when we do calculations, water is really not, shouldn't be included with any part of the calculation. And if it's not there, you might not include it where you shouldn't. And sometimes when people put it in there, they sometimes include it when they maybe shouldn't with the calculation. Now, a base, on the other hand, are things that have the ability to produce hydroxide ions in solution. And much like the acid, what we're talking about here is something that has the ability to produce free OH minus ions in solution. Now, there are strong bases, for example, and a lot of our strong bases come from group 1 and 2 on the periodic table. And that is because group 1 is the alkali metals, group 2 is the alkaline earth metals, and the word alkaline means basic, and that's where a lot of our strong bases come from. Things like sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide. So things like sodium hydroxide, for example, is a strong base. Now, something like sodium hydroxide, all it really has to do is go for a swim, and because it's a strong electrolyte, it will 100% break apart in solution into ions. And you'll have sodium ions floating around and hydroxide ions basically floating around. So if you took like a beaker and you threw some sodium hydroxide in there, it is going to completely break apart into those ions. You will have none of the sodium and hydroxide units sealed together. It's going to completely break apart. And as you can see here, it will form a lot of free OH minus really, really quickly. And that's why it's considered a strong base, because basically it just has to jump into the pool to produce that hydroxide. Now, there are bases, just like there are acids that are strong and weak, there are bases that are weak bases. And ammonia here is probably your popular weak base. And ammonia here does not actually carry, if you will, hydroxide with it. Unlike sodium hydroxide, which has the hydroxide with it, it just goes in, it produces hydroxide. Ammonia doesn't have it. It's got to do a little work to get it. It's got to go find some water and do a little reaction. And when it reacts with water, it will actually, as we will talk about a little bit more, it will actually take an H plus from water. And the result of that is it has the ability, as you can see here, to actually produce hydroxide, which is why it's considered a base, because it does have that ability to produce hydroxide. It will not produce anywhere near the amount of hydroxide something like sodium hydroxide will, because again, it's kind of carrying this hydroxide with it. It's just going to break apart and produce it really, really fast. So there are strong acids and strong bases, and also weak acids and weak bases. And these things, again, are considered electrolytes. And a reminder that if you have a strong electrolyte, that again is going to 100% break apart. It's basically a one-way street, right? Nobody's coming back the other way. If you have something like a weak electrolyte, like a weak base, like we see on the bottom there with ammonia, you can see the arrows heading in both directions, right? So that's a two-way reversible reaction, like we were talking about with equilibrium, that basically happens. Now, a more general definition of an acid and base is the Bronsted, and I really should put his name back on here. I don't know how it got cut off, but it's the Bronsted-Lowry definition of a acid or base. And the Bronsted-Lowry definition of an acid and base is this. A Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. A proton is an H plus, and it's called also a proton because hydrogen has one proton and one electron. How many neutrons does hydrogen have? Zero. Yeah, so it has no neutrons. So the only way you become positive is you lose an electron, which leaves hydrogen now with just a proton, which is why it's sometimes called a proton. And it's important that when you think about gaining or losing an H plus, that because it's not just a hydrogen, it is a plus there. The charge of everybody changes because of that. So if you lose an H plus, you then become one more negative. You think about it, right? If you lose a proton, you now have more electrons, right? So you become more negative by one charge. And if you gain the H plus, you now gain like a proton, which means now you have more protons than electrons. You become one more positive. So very common people screw up the charges on these things. They just think about hydrogen, but again, the charges of these things will change as well. Now, sort of a consequence of the Bronsted-Lowry definition is it will actually make some pairs on the other side that are related to each other. So in this particular case, what's going to happen, as I mentioned, is the NH3 is going to actually accept the H plus, and that's going to make our NH3 our Bronsted-Lowry base. Water in this case is actually going to be our Bronsted acid. When it does so, it will create partners on the other side. And if we come this way, The NH3's partner is NH4 plus on the other side, and this is what is known as the conjugate acid. And water's partner on the other side is going to actually be OH minus in this case, and its partner would be known as the conjugate base. So sort of the consequence of the Bronsted-Lowry definition is you'll actually create partners on opposite sides of the arrow, and they are related to each other. How are they related to each other? They are related to each other by this, just one H plus difference. That is the only difference that there can be in order for them to be related to each other and be referred to as conjugate acid-base pairs. And when we go from the base to the conjugate acid, because the base accepted the H plus, it will have one more H plus as you go to the other side. And because the acid gave away its H plus, as you go to the conjugate base side, you'll have one less H plus. And again, that absolutely positively should be the only difference between things that are considered partners is one H plus. If there is something that looks very similar to each other, but the difference is more than one H plus, two H pluses, three H pluses, however many H pluses there may be, it is not considered a conjugate partner pair there. Any questions on that there? By the way, we saw as well, we could apply this to our acid dissociated in water. If you did put the water in there, for example, actually one-way arrow, you would get again our H3O plus and our Cl minus. And once again here, when we look at this case, we're going to send the H plus over this way. And our hydrochloric acid, as no surprise, is going to be our acid. Water in this case is actually going to be the base in this case, is going to accept it. And that will create our partner on the other side here for HCl, which is the Cl minus. And this is our conjugate base. And our water's partner on the other side here would be our conjugate acid, which is our H3O plus. Once again, it is only a difference of one H plus when you do it as well. This also brings up a pretty interesting idea, as you can see in these two examples. Our friend water in one case acted as an acid, and in the other case acted as a base. And there are substances that can actually do both things. In certain situations, it can act as an acid, and in certain situations, it can act as a base. Those are what are known as being amphoteric substances. Those are guys could act either as a acid or a base, depending on the situation. Water's an example of that. Also, if you have anything with like a hydrogen and like a negative charge, that guy has a hydrogen that it could give away, which means it can act as an acid. It also has the ability to accept a hydrogen as well. So those things typically have a negative charge and a hydrogen. A lot of times also are amphoteric, and they're able to kind of work both ways, can act as an acid or a base. Any questions on that there? All right, so take a moment here for each of these. We want to determine, are these a conjugate acid-base pair? All right, let's take a look here and see. So what we're looking for really are these guys related to each other? I'm just going to write it like this. And what we're looking for, again, is just a 1 H plus difference between them. And obviously there is an H plus difference between these guys, but there is also an oxygen here that obviously this guy doesn't have. So that would mean they are not related to each other, and they're not conjugate acid-base pairs. Now we take a look at the next one, which is this and this. And is this a pair? The answer is the difference between these two is two H pluses, which means they are not pairs either. Again, it can only be one H plus difference. They are related to each other, obviously, but again, it is more than one H plus difference, so they are not considered pairs. We come over here to our NH4 plus and our NH3. In this case, these guys are related to each other. The only difference is one H plus. You could either put the H plus on here, you get this guy, or remove the H plus from this guy, you get this guy, however you want to look at it. But that would be a winner there. Here we have H3O plus and OH minus. Again, the difference here is actually two H pluses, right? So it is not related to each other and clearly not none of the above. So it looks like three is the only one related. Now, to answer maybe a question you might have, why are these guys really not related to each other? This is a diprotic acid, and hydrogens actually come off one at a time. They don't all just drop off. So, for example, if you had sulfuric acid, the first thing that would happen is it would drop one hydrogen and it would make HSO4 minus. The next thing that would happen is the HSO4 minus would then lose a second hydrogen and make a little sulfate action happening here. Do you think it's easier to remove the first hydrogen or the second? Which one should be easier? It is the first one. It's neutral, right? And then after you do that, you now have something with a negative charge that you're trying to rip off a positive, right? So it's going to be a little bit harder, right? Because they're going to be kind of attracted as well. And it is definitely much harder, as we'll talk about towards the end of this part of the chapter, to rip off that second one. Now, that is why if we take this guy and this guy, they are partners. The difference there is only one H plus. If you take this guy and sulfate, they are partners as well. But if you leapfrog from there to there, they are not partners because, again, it's now a two-step difference there along the way. Any questions on that there? All right, so we have aniline. It's isolated. We're looking for the formula of the conjugate acid to this base. So what would it be? Imagine perhaps the winning answer should be up there somewhere. Okay, so hopefully you know it should be an H plus. And the key on this one for people is should you put it on or should you take the H plus off? So a good thing to think about sometimes is one step backwards from what you're looking for. So we have an acid and a base, and we have on the other side our conjugate base and our conjugate acid, right? And by the way, acid and bases just by themselves on the left-hand side of the arrow are your conjugate partners, always on the right-hand side of the arrow. So in this particular case, we're looking for the conjugate acid, which is over here. So if you are not sure what's going on, you could go backwards and go, what you are looking at is actually a base. And the definition of a Bronsted Lowry base is it should accept the H plus. So that would tell you that you should put the H plus on, and you should end up with C6H5 NH3 Na plus. Again, a reminder that the charge does change with it. That is 2, I think, if I'm not mistaken. There would be our winner on that question on that there. So if we have something like HCO3 minus, and I want the conjugate acid, and I also want the conjugate base for this guy, what would it be? Take a moment there, starting with HCO3 minus in each case. All right, so let's take a look. Once again, it's put the H plus on or take it off here. So we'll start with on the right-hand side, we're looking for the conjugate base. That means I want to end up here, which means what I am staring at this point is actually an acid. So again, the definition of an acid is it will donate the H plus, which means we will end up with this guy when we minus an H plus coming this way. I also want my conjugate acid, much like the problem we just did. So if I want my conjugate acid going backwards, that means I am starting with a base in this case. And definition of a base is it's going to accept the H plus, and that means I would end up with H2CO3, no charge. Again, the charge does change. Loss in H plus becomes one more negative. Gains in H plus becomes positive here, right? One more positive, plus one, and minus one is zero. No charge overall on our guy over there on the left-hand side. Any questions on Bronsted Lowry acid base conjugate pairs? All right, we'll lay it up there. See everybody.